In part 2 of this lecture, I will cover the predictive analytics process, starting from defining a problem to developing a model and validating the model and results. In general, the predictive analytics process comprises of 4 basic steps. While these 4 steps are kind of mandatory for solving almost any predictive analytical problem, there could be more steps depending on the nature of the problem that is being faced. The first step in this process is defining the objective. Here, what we do is we interpret a business problem as an analytical need. The way this is done is through a very good understanding of the organization and the industry in which the organization operates. Often there is a need for deep domain knowledge to successfully accomplish this step. Once the problem has been interpreted as an analytical need, there is a need to select a tool and overall approach that is appropriate for solving the problem. An important question that may arise is a predictive analytical solution actually required? Could it be done through a simpler process? The second step is data preparation. Here, we do the hard task of understanding the data, what the data is, where it is coming from, and how it is generated. This step also involves collecting and cleaning the data. Remember the ImageNet project? There were 48,000 MTurk workers working on creating the label dataset. In this step, we also need to create the appropriate data structures. That is, if the data is unstructured, we need to convert it into a structured format, which can be handled by by the analytical models that we develop. The third step is the fun step of building the models and doing the analytics. This involves building regression models and other ML models. There are several analytical models available these days, ranging from very simple naive Bayes to very complex deep neural networks. The fourth step is validation and deployment. Validation is a step that can kill all the fun that you have had during the modeling and analytical part. It is where you actually figure out if what you're saying is robust and valid or not. Once you're sure of its validity, you need to do some analysis on the relationships that you've found. If you've found some association or relationship, you need to kind of interpret them as and understand why they exist in the first place. There are some common business use cases for predictive analytics. These can be generally grouped into 3. The first group comes from customer analytics, where predictive analytics is used for sales forecasting, for building recommendation engines, for understanding customer behavior and their sentiment, for figuring out customer segmentation and market baskets. In fact, some of the common analytical models came out of a need to understand customer behavior. The best example for this is association rule mining, which is also called market basket analysis. It was developed to understand which product should be stacked with which other product in retail stores. One of the most infamous examples of these associations is the association between beer and children's diapers. In some retail stores in US, it was found that the purchase of beer on Friday was associated with the purchase of children's diapers. Can anyone figure out why this is happening? The second group of use cases comes from the manufacturing and operations domain. Here, predictive analytics is used for operational risk assessment, for preventive maintenance, and for resource optimization. One of the best examples for this is the use of predictive analytics at UPS, which resulted in an understanding that left-handed turns in US was generally less efficient and consumed more fuel. The third group comes from finance, wherein predictive analytics is used for predicting the behavior of markets or agents, for portfolio and asset management, and also for fraud detection. Let us go through a few examples that clearly show the need and impact for predictive analytics. The first example comes from a large telecom provider in the United States. This telecom provider, let's call it Telcorp, increased the maximum speed for customers subscribed to their premium internet plan. This was a promotional move developed by the company. A press release was launched, and social media messages were posted by the company to tell this promotional campaign. However, surprisingly, during the first 24 hours, the call centers observed a marked increase in the customer complaint. And the customer churn rate, which was expected to decrease, then showed a marked increase, which was 5 times higher than usual. In the next 24 hours, the customer relationship management team, or the CRM team, monitored the social media messages to figure out what was actually going on. Their analysis figured out that the problem was in the fact that only 20% of the customer base is qualified for this promotional campaign, and somehow the remaining people, the 80% of the people who are subscribed to the non-premium plans, were quite disgruntled, and they were disgruntled to the extent of terminating their plans. After 48 hours, the damage control began, and the increase in speed was rolled out for all the customers all the customers in the organization. The final damage, the final repercussions was that after 48 was that there was an estimated loss of about $110 million as in lost revenue during the first 12-month period. So what do we learn from this? Well, the first thing is even a response after 48 hours is also too slow. And the need of the hour, the business need of the hour is real-time monitoring and sense making from social media. So the second example comes from a well-known company, Gap. I'll start with a question. Which of these two logos do you like? The one on the left with the blue square, or the one on the right? So in 2010, Gap decided to redesign the logo from the one on the left, which is well known, to the one on the right. The change prompted a public protest with more than 2,000 comments on Facebook criticizing this decision. In fact, it became a bit of a joke with a Twitter account set up to protest the change in logo. There was also a site called Make Your Own Gap Logo, which went viral with several parody versions of the Gap logo. After 1 week, Gap decided that it was a huge mistake and decided to revert back to their old squared logo. Since then, this logo has been considered as one of the worst logos of all time. So what do we learn from this? Gap missed understanding the customer sentiments and emotional attachment to the old logo. The business need at Gap was proactive decision making through sense making from social media. In each of these examples, sense making from social media could have been used proactively to inform decision making, or even reactively as a part of a real-time monitoring strategy. However, enhanced sense making requires a lot of social media analytics, specifically related to text analytics. So the step 2 of the predictive analytics process is data preparation. Over here, we not only collect data, but we are also responsible for converting unstructured data to structured data. Structured data is tabular and very predictable. It looks like a nice Excel sheet as you see in the image, in the slide. In the column headers define what kind of data is held by each column, while the row headers provide information related to the data in each of the row. On the other hand, unstructured data is unpredictable and often visual. It is a mix of text, voice, certain scripts, and even images and videos. So the the best most of the web pages are unstructured. While it seems to be very easy for humans or users to understand and interpret, it seems to be very intuitive for us. For a machine, it's very hard to interpret it. Machines like this tabular structure, wherein data is well defined through something known as metadata. The same web page that you see in the image on the bottom left, converted to a structured data, would look something like this. Over here, you see a nice dictionary format with the left hand describing the nature of the data, and the right hand side giving the value of the data. So the login is the metadata, or it's what the data represents, and the right hand side IBM refers to the actual data itself. The examples that I've shown below is from actual websites. It is from a website called github.com, wherein most of the open source software development happens. So let's go to the website itself. So the website for IBM on github.com looks something like this. So this is a very visual website, and as a human looking at it, it seems very intuitive. It just tells us the different projects that IBM hosts on github.com, the different open source projects, the different people who are working on it, and some other information about each of those projects. Fortunately, github.com also provides the same information through a web API. The link for the API is api.github.com.orgs.ibm. Over here, the same information is provided in a structured format. It looks more like a dictionary, with the left-hand side describing what the data contains, and the right-hand side containing the value, containing the actual data value. The third step of the predictive analytics process is modeling and analytics. When you consider the analytical models available, we can group them into two types. One is the regression models or regression techniques, and the second is machine learning techniques. In regression, we try to investigate the relationship between a dependent variable, which is sometimes also known as target or outcome, and the independent variables, which is nothing but the predictors or predictors. Over here, the objective is to find the best fit equation that represents the influence of the predictor on the outcome variable. For example, assume you want to figure out if an increase in the average driving speed results in an increase in the average number of road accidents. This is an analytical problem best solved through regression. The first consideration you have when you're trying to build a regression model is the type of dependent variable. This dependent variable could be continuous or it could be discrete. That is, it has just 0 or 1 value. In our example, the relationship between average driving speed and number of road accidents is the dependent variable, and it is a continuous variable because it can be 1, 2, 3, or whatever. The second consideration is the shape of line or the functional form of the relationship. Do you expect the relationship to be a straight line or a linear relationship? Or do you expect it to be non-linear, having a different form like, say, exponential, logarithmic, inverted U, and so on? In our example, average driving speed and number of road accidents, what do you expect the relationship to be? The linear regression is the simplest form of simplest regression model available. Here, the relationship between the dependent variable or the outcome variable and the independent variable is best described using a straight line. It is represented by an equation y is equal to a plus b into x plus e, where a is the intercept, b is the slope of the line, and e is the error term. For example, let us assume that the relationship between the average driving speed and number of accidents is a straight line. Then the relationship could be something like this. Number of accidents equals to 1.5 plus 0.25 into average driving speed. When we look at the data, the data points that are gathered may look something like this. And when we fit the linear regression line, it will look something like the red line in the right-hand side of the bottom image. Regression models work very well when you're sure of what the relationship looks like. If you're sure that it's a straight line between the dependent and independent variable, then it's very easy to build a linear regression model surrounding the data. But the problem emerges when you do not know these sort of functional relationships. You do not know the mathematical equation that relates the dependent and independent variable. For example, in the ImageNet project, you were trying to figure out what objects exist in an image. It is quite hard to figure out the mathematical equation that can create this sort of relationships. So in these instances, we should allow the data to determine what the relationship looks like. And these kind of data-driven approaches are referred to as machine learning approaches. So basically, machine learning approach is a data-driven approach that identifies a relationship without specific instructions or without knowing the functional form of relationship between the dependent and independent variable. The sample data that is used to develop the model or relationship is called the training or label data. In the ImageNet project, the label data comprised of over 1 billion images that was manually coded by MTurk workers. Using those example data or using the training and label data, we learn the relationship between the outcome or dependent and independent variables. Let's take the example, let's take a famous text analytics example that is trying to understand the sentiment of a sentence. Or in other words, trying to figure out if a sentence has positive sentiment or a negative sentiment. This kind of example is a perfect machine learning problem. There are two ways we could solve this problem. The first is referred to as supervised machine. The first is by using supervised learning. In this case, you are privileged with an existing data set, or you are privileged with the label data. In the ImageNet project, the label data had to be created by MTurk workers. And in our textual analytics example, we could collect the data from say reviews or ratings of reviews and so on. So using this label data, we can build the classification model. We can build a model that relates its whether that tries to understand whether a sentence has a positive or negative sentiment. Supervised learning could be of two types. It could be a classification. It could be a classification model when the outcome variable is discrete. That is, in our example of sentiment, there is only two values, positive and negative sentiment, and hence it is discrete. Or it could even be a regression as well. depending on how well you know the functional form. If you do not have the privilege of a labeled data set, then you have to depend on another group of machine learning techniques referred to as unsupervised learning. In this case, we allow the data to even define what the outcome variables will look like. We do not even know that there are positive and negative sentiments. We just have a set of sentences, and we try to group them into different categories. So if so, one of these in our text analytics example, what could happen is we could cluster around specific words. Like we could expect that positive sentiment sentences would cluster around words like mother, father, and so on. The most common unsupervised learning approaches are clustering and association rule mining. The last step of the predictive analytics process is validation of the analytical model. Usually, the validation involves two big steps. One is understanding the goodness of fit, wherein we see if the model developed is complete. Are we missing something very important? Are we missing some very important data that we didn't have when building the model? So this goodness of fit is done by understanding the percentage of variance that is explained by the model that is developed. Some of the common metrics that is used to understand the goodness of fit is R square, adjusted R square, error terms, and so on. The second big important validation test is with regard to predictions or with regard to precision. Basically, here we are trying to understand if the prediction is accurate. To do this, we divide the data set into, or the training data set into two groups. The first set is the training data set, which is used only for the purpose of building the model, only for the purpose of understanding the relationship between the outcome and the independent variables. We then use the testing data set to validate if the model developed is actually predicting the right outcome or not. Some of the metrics that is used is accuracy, recall, F1 scores to understand how good the model is in prediction. For a really, really important step, this slide is surprisingly empty, but the reason for this is that although these two terms cover most of the important validation aspects, the details of these validation aspects have been left out. So finally, in part three, finally we move on to part three of this lecture. Here I will introduce certain technical aspects, and I will talk about how Python can be used for predictive analytics. This part will be covered in the in-class session on Monday. So I look forward to seeing you or meeting you on Zoom on Monday for part three. Thank you.